The embedded system which we designed is a solar tracker.
The objective of this project was to design and build a mechanical device which uses a digital microcontroller, in this case the Arduino Due, and light-dependent resistors to track the movement of the sun across the sky. This device would sense variation in light levels and rotate to maintain direct alignment with the sun. The solar tracker uses two servos for rotation and logged rotations and solar data to a smartphone using the Seed Studio Bluetooth shield.
The solar tracker circuit has two main hardware constituents, the rotating array and the comparator circuit. The rotating array utilizes two servos, each connected to a gear belt, to tilt the top panel in four directions, north, south, east, and west. This tilting is enabled by a ball and socket joint underneath the top panel. The two 12-volt 1-amp servos are controlled by a DF robot motor shield using an L293 integrated circuit chip. This shield, along with the Seed Bluetooth shield, are both connected to the Arduino Due. Furthermore, the amount of tilt is determined by the four equally spaced light-dependent resistors surrounding the opaque object at the center of the top panel. Each LDR forms a voltage divider with a 10 kilo-ohm resistor. A differential amplifier then compares the voltage drop across the north and south facing LDRs, as well as the east and west facing LDRs. Another key aspect of the comparator circuit is a voltage buffer with unity gain, which establishes a 2.5 voltage reference for the single supply op-amps, enabling them to be powered by the 5-volt supply available from the Arduino Due. Rail-to-rail op-amps were also used to enable a larger output voltage swing when powered by a single supply. These two images demonstrate the proposed design of the solar tracker. The image on the left shows the complete apparatus, while the image on the right shows the light sensor with four light-dependent resistors around an opaque object. This is the complete comparator circuit schematic for the solar tracker, as well as the circuit analysis calculations. The voltage buffer to establish a 2.5 reference, rather than a 0-volt reference, is the leftmost op-amp. The output of this buffer is then used by two differential amplifiers with a gain of approximately 1/3. This gain was chosen so that the output of each diff amp would never surpass the 3.3 volt maximum input rating of the Arduino Due pins. The first issue we encountered when designing the solar tracker was that the Arduino pins cannot take an input greater than 3.3 volts. This altered the way in which we were mapping analog voltage readings to digital values from 5 divided by 1023 to 3.3 divided by 1023. It was also necessary to track the position of both servos to prevent over-rotation, which would cause the gear belts to slip or bend the top panel. Each servo rotates 1 degree in 23 milliseconds. It was determined that once a servo rotated 180 degrees in one direction, it would reset to its starting position. The servos will rotate until the voltage across a pair of opposing LDRs is equal, at which point the rotation will stop. When testing the comparator circuit, we primarily used a flashlight to simulate sunlight and covered the LDRs completely to simulate darkness. Under these conditions, the circuit worked properly. However, when we began to test using ambient light, we noticed that the circuit was unresponsive to light to moderate shading. This was because, in typical lighting, the LDR voltages were in the millivolt range. However, under a flashlight or in complete darkness, the LDR voltages were 1 to 2 volts. A millivolt input to the differential amplifiers was not enough to drive a changing output. Therefore, the comparator circuit was removed and the four LDR voltages were directly input to the Arduino. Voltage comparison was then performed within our code rather than our hardware.
The program written for the Arduino Due can be divided into three main functions. Firstly, it must receive and process data from the sensor circuit, which is connected to two analog pins. Secondly, it must use this data to make a decision on which direction the servo motor is turning. Then, when polled by a paired device, it must send this data over Bluetooth. The data used includes the north-south voltage, the east-west voltage, both from the sensing circuit, the number of rotations done by the motors, the angle of the motors, and the response time. We can also use dummy data from a reputable source to project the system performance and the total energy production per day. The Arduino Due utilizes a SAM3X microprocessor. The SAM3X possesses many capabilities which allow the hardware to be effectively manipulated. The peripheral input and output allows the Due to receive input from the light-dependent resistors and output data to the motors. Notably, the SAM3X possesses multiple USARTs. In this case, we are using USART1. This allows serial communication to the connected PC and the paired Bluetooth device in the same program, without the use of the software serial library.
All issues encountered with the solar tracker were first assumed to be hardware related. Therefore, the external power supply and power rails were checked. Node voltages and output voltage levels were also read using the digital and analog discovery. Finally, the documentation of the motor shield was used to ensure that proper connections were being made between the hardware and software portions of the project. If there were no apparent hardware issues, then the software was debugged by checking for errors in the code and printing intermediate variables to the serial monitor. The assert.h library was also used. Additionally, small portions of the code were run individually to check specific processes. For example, testing the code from the north-south for the north-south rotation separately from that for the east-west rotation. Alright, so this is our solar tracker. On top we have our 4 LDRs with the directions labeled and our little opaque cardboard set up in the center to shade the different LDRs. Down here we have the Arduino Due with the motor driver and the C Bluetooth shield. This was the comparator circuit that we're no longer using. The only parts that we're currently powering with 3.3 volts are the voltage dividers that the LDRs need. Currently we have both motors turning, and then Savith, if you want to just like apply a little light over the top. Alright, so east-west has stopped, and if we keep shifting, try going the other direction. Yeah, okay. And so at this point, we have the light basically directly above the LDRs, and we have both of them stopped. We detached the drive belts just because it's easier to shift a light for the short length of this video. We also have connection to a phone with Bluetooth, and this is the data that we're currently outputting through serial that eventually will be sent to the smartphone when the user sends a character to